Hi there and welcome to this session on dew points. Now, my name's Darren and I'm going to take you through this pretty quickly. And what am I talking about? Well, if you're in a wall system or indeed in a roof system and you've undertaken a thermal count, for example, you may want to expand on that to have a quick check on its dew point. And that is directly referencing the interstitial condensation that may occur within the system. So we have another selection field here called dew point, and this is based on something called the Glaser method, which is embedded within an international standard called ISO 13788. Clicking on that allows you to see a form. But before we dive into this, let's go ahead and have a quick look, 5 minutes or so, on this standard, because it's pretty important to understand the basics, at least from an external condition, internal condition, and what that layering there means. Okay, so here is ISO 13788 in all its glory, and fundamentally what it is a standard that details calculation methods for hygrothermal performance of building components and elements, as you can see there. It focuses specifically on determining the internal surface temperature required to prevent critical surface humidity and interstitial within systems, say wall systems, roof systems, for example. It's not the newest standard, and it is somewhat outdated. It was originally published back in 2001, I believe, and it was republished in 2012, which is this edition here. I think this is the latest edition. I might be wrong on that, but I think this is the latest edition. But fundamentally nothing has changed. The equations behind that is provided through this standard have not changed, and that needs to be elaborated on a little bit, because that means that it is somewhat simplified, because it was based on folks doing equations by hand or in spreadsheets, and it doesn't take into account some critical items that you may want to consider when you're undertaking hygrothermal assessments. Let's go ahead and find the scope and limitation section. Okay, here it is, and let's go see exactly what it says. So, the assessment of risk of interstitial condensation due to water vapor diffusion, that's what it's aiming to do. The method does not take into account a number of important physical phenomena, including the variation of material properties, which material properties will vary significantly in terms of their moisture content, capillary suction and liquid moisture transfer within materials. So it's really just a vapor diffusion method rather than taking it into account any other naturally occurring moisture transfer mechanisms that occur in buildings. Air movement from within the building into the component through gaps or within air spaces, so that's not taken into account, which is very, very important. Incidentally, that's not actually well taken into account in dynamic hygrothermal simulations as well. And then we've got the last one there, the hygroscopic moisture capacity of materials. So what do you take from this? Well, you take that it's fundamentally a simple standard that doesn't cover quite important aspects of design. Arguably, this is more reliable for lightweight, airtight structures without materials that store large amounts of water. And please bear that in mind. Now, if you are operating in a climate, within a building code, please make sure that you are able to use this standard. I could state that in Australia you would not be able to use this standard anymore. It has been completely displaced by the DA07 standard for dynamic hygrothermal simulations. But that doesn't mean it can't be used. And it probably can be used in climates that are constantly requiring buildings to be warmed in the inside and are not very kind of dynamic buildings, so they're quite stable. So you could look at this in a very cold climate from a residential point of view. So the South Island in New Zealand, for example, you could feasibly use this and get some value out of it. That being said, there are major things here that are not included, but you could get value out of it. I'm not suggesting that you base all your design on this, but if you get something that you have fundamentally thrown lots of moisture into from a theoretical point of view in a calculation, and it works, then you're probably in a position where doing something more complex and detailed in a dynamic hygrothermal simulation over 10 years, for example, would probably work as well. So let's go and have a quick look at its key concepts, because there are lots of detail within here, and this part of the course is not to explain every single detail in here. We've tracked against the calculation requirements of the standard itself, but the important components for you to understand from this is what you need to consider when you're undertaking calculations on the platform. And they are primarily your external environment, your internal environment. You want to make assumptions about those because they carry moisture and they carry temperature profiles and relative humidity profiles. And once you account for those, then you'll be in a position where you can ascertain the risk of condensate occurring on the surface of a material within a wall, for example, within a roof, for example. So let's go ahead and I'll go and find the key concepts and come back. Now here in section 6.4.3 it provides a bit of an overview about what's happening under the hood in better building when you undertake a G-point assessment. So starting with any month of the year, and it's called the trial month in the standard, we go ahead and calculate the temperature, the saturated vapor pressure, and vapor distributions throughout the component. So if it's a multi-layered component, we do it for each component within that multi-layered system. And then we determine whether any condensation is predicted. If no condensation is predicted in that trial month, then we repeat the calculation with successive following months until either no condensation has been found in any of the 12 months, and then report the component as free from condensation, or a month is found with condensation, and then this is the starting month. Now, if condensation is predicted in that trial month, or in the trial month, we repeat the calculation with successively earlier months until either condensation is predicted in all 12 months, then starting with any month, calculate the total annual accumulation of condensation, or a month is found with no condensation, and then take the following month as the starting month. In a nutshell, this allows us to go ahead and generate a profile across the course of the year where condensate occurs or doesn't occur, and at what point it does occur. And I'm going to go ahead and find probably the most useful diagram to explain this. But if you have your two curves, so you have your vapor saturation curve, and there it is there, and it doesn't meet this curve here, then there is no condensate theoretically being formed. However, if you do get a curve such as this PS and it meets the vapor pressure, then it is deemed to occur. So there is a condensate occurrence, and then that has a rate which is defined there. we'll see this in more in action when we jump back onto the platform. Now, that's fine, that's all interesting, but we need to jump down into the annexes to really understand how to set up a model in Better Building. We're going to set up a model relative to its internal boundary conditions. And I forget what the external boundary conditions are, but they are sought for you through a climate file pertaining to your project location. Now we'll see this in a wee bit, but you can select, if you want to, an internal boundary condition based on a point 1 here, which is continental and tropical climates. And as stated here, in the absence of well-defined, controlled, measured or simulated internal air conditions, a simplified approach can be taken, and this is a way to take that simplified approach. So with the lack of better data available, you can take this approach here, and this is where the internal air conditions are derived from entering the daily mean of the external air temperature into the graphs as per here. Okay, so that's provided for you, and then you've also got conditions for maritime climates, which is handled slightly different, where if you select you've got maritime climates, which might be applicable, then you can go ahead and say, hey, my internal humidity can be determined based on a humidity class from 1 to 5, as you can see here. So I think we always default to 3, but if you don't know, go a little bit higher. Humidity class 4, representing a sports hall condition, sports halls, kitchens or canteens, and effectively this graph then allows us to ascertain the humidity class that is popped into your model. Okay, so once that's popped into your model, then we go through the step-by-step process of running the assessment in order to ascertain whether there is condensate in the system and for how long it occurs and for what rate it occurs at, and even whether it theoretically dries out or not. So let's jump back to the platform now, and we're going to go and have a look at how this transpires when you're doing the simulation itself. Okay, here we are. Let's zoom in a wee bit and talk about this system here. It doesn't need to be this system, it can be any system. I might go ahead and pop on an additional air membrane or something here, just to make a point of a system that may fail. I'm just going to put a class 3 vapor permeable membrane there, and I've already got 2 layers of fire rated plasterboard there. So there's quite a bit of theoretical vapor resistance accumulating there at the front of the system, so I'm kind of setting up a system to fail a little bit. It may not fail because of the climate that it happens to be in. I should probably say that ISO 13788 is not great in terms of warm climates, mainly focused on colder climates. So let's go ahead and rectify that, and we're going to update this project quickly to be in a colder climate, let's say Hobart. Okay, update that for good measure. Done. Okay, so now our climate is now much colder and much more appropriate to be using the ISO 13788 standard. So go back to the dashboard, and we'll go and grab that calculation example. Doesn't make a difference which one we do. I didn't save that, so I'm just going to pop that membrane back on there and apply it there. There we go. So do a little save there. So all of these materials have a level of resistance associated to them. We have a slightly ventilated air cavity, we've got a membrane, we've got 2 layers of fire rated plasterboard insulation, and some plasterboard on the inside. So once we go to select dew point, we get to see this form again, and we get to identify the external conditions pertaining to the assessment, the internal, and layers. Layers are not too important for you. But now this is in Hobart, we can then say, okay, do we want for the external conditions to be the monthly mean of the daily minimum, the monthly mean or a fixed value. We tend to just pick the monthly mean, and that directly relates to the ISO 13788 standard. And then should you want to change that temperature, we do provide an opportunity to shift it away. So if you do want to make it a little bit more conservative, because this is probably, that's going to be based on maybe 10 years of data, and we do find things are getting both colder and hotter, then you may want to adjust that accordingly. The same is true for relative humidity on the external side. Pick a winner in terms of your strategy, but if you want to bump up the relative humidity in the climate file, you're more than welcome to do so, and we do recommend that you do that because it makes for a much more theoretically durable system if you're more conservative, i.e. colder and more moisture in your sims. However, just do bear in mind that these sims are more interested in the vapor coming through from the inside to the outside, so it may not make a huge amount of difference, but it depends how you nominate your internal conditions. Because if you nominate a fixed condition like this, where you got 20 degrees and fixed indoor relative humidity, that's fine. That's fixed. It's not related to what's happening on the outside. But if you go ahead and nominate a Annex A.1, which I showed you there a second ago, then you are effectively getting your temperatures based on the outdoor temperature. So completely up to you how you want to do that. That may be a way to do it. And then again, you can change those temperatures again. For the relative humidity, we have both the Annex A.1 and the maritime climates. And this is where you can set those occupancies up should you wish to make a call on the humidity class associated as a function of what's in the code. You'll be able to look in our documentation for more information on all of this. We've presented it. Just do a little search on whatever humidity class and it will pop up. And then for layers, this is just a really kind of detailed approach in accordance to the standard, but it states that it is recommended that elements with a thermal resistance greater than 0.25, that's an R value there, are subdivided into a number of notional layers, each with thermal resistance not exceeding 0.25. So anyway, so if you want to nominate that based on that rule set, go ahead and just nominate it. If not, feel free to leave it. But that's all there is in terms of running the simulation, and in terms of the getting some results up. We can just hit create and then it's locked in, and then all we've got to do is click run one simulation and we will see a spinner and ultimately some results. So there you go, that's a bit of a disaster of a result there. So that's a good one for demonstration purposes. We have the dreaded pink. We're looking for green. We've got dreaded pink there. Should you want to go ahead and copy this into your reports or emails, you can. But what does it say? It says, well, the condensation plane has been found at the interface of two layers, and that is the membrane and that kind of bracing board. So the fire-rated plasterboard is there referencing the bracing board. And let's have a look at it. Interstitial occurs within the system, does not evaporate at all. Bad news. So this is an extreme example, and let's look at the summary before we get into this, or let's look at the inputs before we get into it. So this is what we're working with. We're working with dry bulb temperatures where it gets pretty cold, and these are those mean temperatures, and then the relative humidity is moderate to reasonably high during the winter. So that's what you're working with. When it comes to the results, we can look at the summary, and you can go ahead and download this should you want, and provide that to a design team as some evidence that you've undertaken assessment. And what we can see here is to meet the acceptance criteria, which has been set by the standard, condensate must not accumulate over the assessment period. I'd probably argue that any kind of red here in most cases is going to mean that you've got an issue. So it's saying it does not evaporate and consider undertaking a more detailed hygrothermal assessment, which of course you can do, but not the subject of this assessment. We see a summary. We've got the climate data from here. We added in these conditions here. We chose Annex A.1 and we chose A.2 for the internal humidity. And then we get a breakdown of the external temperatures, the external humidity, the internal temperatures, and the internal humidity. So we can see it's hovering up quite high there. And then we get a summary of the peak vapor flow through the system. So I'm going to come back to this in a second because I want to jump into these two areas here, vapor pressure and temperature. So an easier one to look at is probably temperature, where you hover over the respective month and you get the assumptions for the temperature within the system. So we can see that in the peak April, May, it gets pretty cold there. It's at that interface there, it's about 10 degrees. That's pretty cold. Does it get lower? It gets a lot lower, as you might expect. So it gets down to about 6 degrees. So that's telling you that there is a potential risk there because it's cold, and there's also a level of resistance through that class 3 application of a generic membrane. If we go to vapor pressure then, bearing in mind that we've got cold temperatures at that point in the system, we can then go ahead and see where the saturation vapor pressure crosses over with the vapor pressure. So if I go ahead and just toggle that off for a second, that's your saturation vapor pressure, and that's your vapor pressure. And what we can see is that we've actually got 2 points in the system, because we've got a crossover there and a crossover there, and they're both suggesting, yeah, across the year, but arguably on the outside it's probably more frequent, and because of that we can state that there is a likelihood of saturation or condensation occurring because the vapor pressure exceeds the saturation vapor pressure. So that then comes back to the summary here, and we summarize effectively the that peak vapor flow month there in July, just for you to be able to, I guess, see that, and you'll be able to then look at the peak condensate month as well, and you'll see that the condensate value there is stipulated in grams at the exterior kind of framing, so it's right there on the outside. That's probably more of the issue there, that you've got condensate occurring at the membrane layer next to the bracing. But there you go. Once you're happy, you can, of course, go ahead and download. Let's see, we can download the report, and if you have a theme, go ahead and use that theme. If you don't know what themes are, go ahead and take the course. They are effectively ways where you can remove the better building, or once called speckle branding, and replace it with your own branding. And that means that you can change your logos, you can add new logos, you can add new points of references, you can change the fonts, you can change the tables, change the layout from portrait to landscape, etc. Once you have your theme in, we also strongly recommend that you go ahead and take that last step and fill out this form pertaining to project information. Who are you, the modeler? Who's reviewing? Who is the building owner or building representative? All of this is framed up from a building surveyor's perspective, or building certifier's perspective, depends on where you are. And this is additional information that may be useful. So arguably for dew point assessments, these are quick checks, so you may not need to use all this, but please be aware that if you do fill this out, it does give folks a bit more confidence that you know what you're doing, and it gets popped in to the beginning of the report. So click and create will generate that report. I'll go ahead and do that now. Okay, and there it is. So I've used a landscape template that I was working on. So it's not necessarily going to look like this. It's not necessarily going to have the same watermarks. It's not necessarily going to have the same layouts, but it will have the same level of information within the model, your assumptions, your limitations, your inputs. So important information about the materials that have been used, because we have assumed the vapor resistance of the materials for you based on our own experience and the generic materials. If you were to use a material from a supplier, you would be adopting their tested vapor resistance in most cases, unless we've worked with them to specify vapor resistance themselves for a typical product similar to their product. But yeah, everything else is popped in there for you, and you get your results and should be able to provide this to any design team in order to explain what's going on in the system. But as mentioned, caveat, please go ahead and make sure that you're fully across the limitations of the ISO 13788 standard. Go ahead, answer those questions. We won't make them too difficult for you, and we will then issue that certificate of competency for you to do with what you want. There you go. That's it. That's a wrap. Thank you very much. See you at the next one.